Okay, so resuming on our discussion of electron configurations, let's look at the electron configuration for bromine as it really showcases something quite important. So bromine is a 7A element. It also, looking in the periodic table, would someone like to tell me what is bromine's atomic number? What is bromine's atomic number?
35.
Yep, exactly right. So then we'd have a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So we've used up 10, 20 electrons. And what orbital is filled? What subshell is filled after the 4s? Yep, exactly right. And the 3d orbital can hold 10 electrons. So we used up another 10 electrons. We have 5 electrons remaining. So how many electrons go into our 4p orbital?
5.
Yep, exactly right. Now, if you wanted to write this as an abbreviated configuration, we can summarize these initial core electrons using the configuration of the preceding noble gas. So this could also be written as argon 4s2 3d10 4p5. Now there are a few things to note here. First, you cannot include these 3d electrons in argon's noble gas configuration. These 3d electrons and the 3d orbital is filled after argon. Further, which of these electrons are valence? Which of these electrons are in the outermost orbital with the largest n value?
4s2 and 4p5.
Yep, exactly right. And if we add up our valence electrons, we see that we have 7 valence electrons. These 3d electrons are core electrons, and they aren't as accessible for chemical reactions. Does that make sense to everyone? Any questions on this example?
Which ones are we adding for the 7 valence electrons?
The electrons in our outermost orbitals, which are our 4s and 4p orbitals, because they're the orbitals that are farthest from the nucleus with the largest n, and so these are called our valence electrons. We don't add our 3d electrons because they're inner shell. They have a smaller n value, and they're held correspondingly relatively closer to the nucleus.
Oh, okay. So the 5 and the 2 is where we're getting
exactly.
7. Thank you.
So let's look at another set of examples, and this one's a little bit, this next set will be a little bit more straightforward. We're asked to write the configurations for each set of ions. Now for ions, you need to be really careful when you're counting electrons. So for example, for O2 minus, oxygen, if we look in the periodic table, if we go and find oxygen in our periodic table, it typically has an atomic number of 8. However, since we have a 2 minus charge, our number of electrons is equal to our atomic number minus the charge, which gives us 10 electrons to work with. So if we find our closest preceding noble gas, that would be helium. And then we fill in our orbitals from the lowest to the highest energy. And as we notice, the configuration for O2 minus matches the configuration for that of the noble gas neon, which is helium 2s2 2p6. So one thing that we've noticed, one common trend that we've noticed in our discussions is that many common ions adopt an electron configuration matching that of the closest noble gas. So noble gas notation or abbreviated electron configurations are really important because they can help you very readily see patterns of reactivity and patterns for ionization. So what I'd like you to do is I'd like you to look at the following 3 cations, and I'd like you to propose an electron configuration for each of the 3 cations. Note, just for completeness, I'd prefer that you write out the noble gas configuration following, I'd like you to write out the noble gas configuration identifying the core and valence electrons, because noble gases being 8A elements will have 8 valence electrons. It's generally not appropriate to just put the corresponding noble gas symbol in brackets. It's sometimes seen when people are writing electron configurations for noble gases, but I'd prefer you write out the noble gas electron configuration such that the core and valence electrons are clearly shown. So let's take about 4 to 5 minutes and let's work through this example, and then we'll come together as a group to discuss. And if you have any questions in the meantime, don't be shy to ask them in the chat or verbally. Additionally, if you have any proposed responses, don't be shy to share them in the chat or verbally. And we'll discuss this example in about 4 to 5 minutes. And let's try to get a few proposed electron configurations in the chat. You may notice many of your electron configurations will be very similar when you're writing the configurations for ions and for species with noble gas-like configurations. And don't be shy to share your responses in the chat or verbally. Or if you have a question, I'd be happy to address any questions as well. And don't be shy to share your responses in the chat or verbally, or ask a question. And we'll discuss this example in another 2 to 3 minutes. And let's try to get a few more responses in the chat before we discuss. And we are starting to see a reasonable pool of responses in the chat. Let's keep working on this and we'll discuss in about another 1.5 to 2 minutes. And as I notice in the chat, students are starting to see that some of these ions have the exact same configuration. And so we have a nice pool of responses. Let's add a few more responses to the chat and we'll discuss in about another 30 seconds to a minute. It's great that I see this pool of responses in the chat and of participation from a wide swath of the class. Okay, so let's discuss. So sodium in the periodic table has 11 electrons to its name. Sodium plus, however, we have to take our atomic number and subtract the charge, which is +1, and that gives us 10 electrons to work with. Filling our orbitals from lowest to highest energy, we have 1s2, 2s2, 2p6, which could in turn be written as helium 2s2, 2p6. If we have a 10 electron structure, it will have the exact same configuration, same number of electrons, same configuration. Does that make sense to everyone? Okay, let's look at aluminum. Would someone like to tell me what is the atomic number of aluminum? We need that to calculate the number of electrons. 13. Okay, so for our number of electrons, we have 13 minus a charge of +3. We have 10 electrons. If we have the same number of electrons, will our configuration also be the same?
Yes.
Exactly right. So 1s2, 2s2, 2p6. And that gives us helium 2s2, 2p6. So as we can see, as we have a noble gas-like configuration, all of our electron configurations for these noble gas-like ions have 8 valence electrons. Let's look at lithium now. What is the atomic number for lithium? What is the atomic number for lithium? 3, okay? But since it's lithium plus, our number of electrons is 3 minus the charge, which is +1. That gives us 2 electrons to work with, or a configuration of 1s2. Does this make sense? Any questions on these examples? So writing the configuration for ions is pretty straightforward compared to neutral atoms. You're often going to notice the configuration for most ions are going to be almost identical. Okay, so let's talk about valence electrons now. Valence electrons are best defined as electrons in the outermost energy level with the largest N value. The valence electrons are also equal to the group number for main group elements. Further, and this is really important, elements of the same group in column, in other words, have the same valence electron configurations and number of valence electrons. And these valence electrons are really important because they're the electrons that are actively being exchanged, gained, or lost in chemical reactions and bonding events. So as a result, elements of the same group have similar reactivity because they have the same valence electron configuration and number of valence electrons. Does that make sense? Same column, same group, same or similar reactivity. So, for example, if we look at the configurations for each of our main groups in the periodic table, we notice that the only thing that changes as we move down the periodic table is that our orbital n value increases. The configuration of our valence electrons in each of our groups is the same within that group. Does everyone notice this clear pattern in the electron configurations and number of valence electrons? So for 1A, we have 1 valence electron. For 2A, we have 2 valence electrons. 3A, 3 valence electrons, and so forth. Any questions on this idea? Okay, so let's keep going and let's talk about isoelectronic species. We commonly see these when we start talking about the electron configurations for ions. So isoelectronic species have the same number of electrons and the same ground state electron configuration. So for example, if we look at each of these ions, sodium plus, F minus, N3 minus, O2 minus, what element are all of these ions isoelectronic with? What electron configuration or what number of electrons matches the number of electrons observed for each of these ions? All of these ions are isoelectronic with the noble gas neon, which has a configuration helium 2s2 2p6. Now this is really important because this can help us to understand a really important pattern in terms of ionization preferences. So just to make sure we're all on the same page, I'd like you to tell me what, one moment. I'd like you to tell me what neutral atom is isoelectronic with H minus. So let's take a moment. I'd like you to figure out the number of electrons that H minus has, and I'd like you to tell me what neutral atom has the same number of electrons as H minus. And let's give everyone about a minute to a minute and a half on this example. And don't be shy to share your responses in the chat. So we're starting to see a pool of responses. So let's talk about this. So H minus, so we initially have 1 electron, we then subtract the charge of -1, and that gives us 2 electrons total. And the element with 2 electrons is helium. So H minus is isoelectronic, has the same number of electrons as helium. So it's isoelectronic with helium. Does this example make sense? Perfect, perfect. So let's talk about noble gases now. They're a really important group in the periodic table. Noble gases, which are group 8A elements, have full outermost valence shells and are more stable and less reactive than other electron configurations. Noble gas configurations, 8 valence electrons, are generally stable. There's one other noble gas configuration we need to be aware of, and that's the 1s2 configuration, which matches that of helium. Now, why is this important? Why does this matter? Well, it is more favorable for atoms to gain or lose electrons if you generate a stable noble gas configuration. Further, it's also relatively easy to lose high energy valence electrons or to gain electrons if you're creating a full outermost valence orbital. So the takeaway from this idea is that atoms will form ions with noble gas configurations. And as a result, atoms will prefer to form ions with their charge equal to the group number if it's a 1A through 3A element. In other words, if it's a metal. While atoms will prefer to form ions with charge equal to the group number minus, in other words, are non-metals. Essentially, we're trying to reach the closest noble gas configuration. So, if we look at aluminum, for example, aluminum is a group 3A element and it's also a metal. So then its charge is equal to the group number, which is +3. To help you visualize why this is occurring, aluminum has a configuration of neon 3s2, 3p1. So how many electrons do we need to lose to get to neon? How many electrons do we need to lose to get to neon? Yes, 3 electrons, exactly right, because this configuration has 3 valence electrons that we need to lose. Does that make sense to everyone? Does this idea make sense that you're losing or gaining valence electrons to reach the closest noble gas? So let's keep going. So oxygen, which is a group 6A, which is a non-metal element, adopts the charge of 2-. Why? Remember, we said the charge preferred for a non-metal main group element is equal to the group number -8. So 6 minus 8 gives us a charge of -2. Does that make sense to everyone? To help you visualize this from the perspective of electron configurations, if we have 6 valence electrons, how many do we need to gain to reach 8 valence electrons? And to help you visualize this, so initially I have 6 electrons, and how many do I need to gain to fill out my shell? I need to gain how many electrons?
2.
2, exactly right. And that gives us 8 electrons. Does that make sense? Is everyone comfortable with these ionization trends? Okay, so let's keep going and let's first start off by writing the abbreviated or noble gas electron configurations for the following ions. I'll start us off O2 minus. Oxygen has an atomic number of 8. 8 minus -2 gives us 10 electrons, and that gives us a configuration of helium 2s2 2p6, which matches the configuration for that of neon. So what I'd like you to do is take about 2 to 3 minutes and write the configurations for potassium plus and lanthanum 3 plus. And remember, start with your electron count and then go from there. And we'll discuss this example in about 2 to 3 minutes, and I'd like to see a few electron configurations proposed in the chat. And we're already starting to see some reasonable responses in the chat. Let's try to get a few more responses before we discuss. And this is really just getting everyone used to writing electron configurations for common ions that they'd see in this class. And for lanthanum, don't freak out that it's in the lanthanides. Just think about your electron count and try to find the closest noble gas. And we'll discuss this example in about another minute. Okay, so let's talk about this example. So potassium, if we look in the periodic table, has an atomic number of 19. To calculate the number of electrons, we take the atomic number minus the charge, which gives us 18 electrons. The closest noble gas with 18 electrons would be argon, which has the configuration of neon 3s2 3p6. Does this first example make sense? So for lanthanum, just counting electrons, has 57 electrons. 57 minus plus 3 gives us 54. The noble gas with 54 electrons is xenon. And xenon has a configuration of krypton, 5s2, 4d10, 5p6, which matches the configuration for xenon. Does this make sense to everyone? Perfect. So what I'd like us now to do is I'd like us to look at the following set of atoms, and I'd like you to predict the preferred charge. So I'll start us off and I'll do one of the more tricky examples. So scandium has a configuration of argon 4s2 3d1. So to reach our closest noble gas configuration, we need to lose 3 electrons. So then scandium will prefer to form scandium 3+. So with that representative example in mind, and with the shortcut equations that I've showed you for predicting charge, I'd like you to predict the preferred charge for ions formed from the following 3 atoms. And we'll discuss this example momentarily. And make sure to note whether the charge is positive or negative. And let's try to get a few more responses in the chat, and we'll discuss this example in about another 2 to 3 minutes. And we're seeing a lot of reasonable responses in the chat. Remember that metals prefer to form cations with a positive charge, while non-metals prefer to form anions with a negative charge.
Professor, how did you get to 3D1?
Because the next orbital that's filled after the 4s is the 3d. And because scandium has 21 electrons and argon has 18, our 3 electrons go first in our 4s and then afterwards into our next highest energy orbital, which is the 3d orbital.
Okay, got it.
Does that make sense?
Yes, I didn't realize, I was counting up to 20, so I didn't realize it's 21.
No problem, no problem. Let's try to get a few more responses in the chat for the predicted charges of each of these ions, and then we'll discuss in about another minute.
Professor, how do we predict the transition elements?
The transition metals have their own set of rules, and the transition metals can adopt typically a variable charge. However, for most of the early transition metals, you can lose all of the 4s and 3d electrons to generate an ion. That's why I showed the scandium example, because it's a slight exception to the rules that we've discussed. So I wanted to make sure that the examples that I have you work on independently are more common charge prediction and electron configuration examples. Did that answer your question?
So we count to see if it's easier for them to gain or easier for them to lose. That's how we know if they
Exactly.
become cation or ion.
Yep, exactly right. And transition metals form cations, but they can lose a varying number of electrons. And we'll actually talk about that in the next chapter, how to handle transition metals and how to describe transition metals so that the reader knows the charge of that transition metal. So long story short, for transition metals, you can either lose all of your 4s or 3d electrons, but transition metals can form a range of ions.
Okay, got it. Thank you.
So let's discuss this example here. So phosphorus is a group 5a element. Just to make sure that we have a nice reference to go off of, has a configuration of neon 3s2 3p3. So using our formula, our charge is equal to the group number, which is 5 minus 8, which would be minus 3. So we'd predict that phosphorus would form the ion phosphorus 3 minus. Why is that? So in order to reach the noble gas configuration for argon, which is neon 3s2 3p6, we'd need to gain a total of 3 electrons. Does this first example make sense? Does this first example make sense? Looking at aluminum, it's a group 3a element, which means it's a metal. So it would prefer to form a charge equal to the group number, which would be positive 3. Why is that? Aluminum has a configuration of neon 3s2 3p1. So in order to reach the configuration of the closest noble gas, we would need to lose a total of 3 electrons. Does this make sense to everyone? Any questions on this idea? Finally, let's look at iodine. So iodine is a group 7a element, and it's a non-metal. So then we'd predict the charge would be equal to the group number minus 8, which would be -1. So iodine would prefer to form iodide, I minus. Does this example make sense to everyone? Everyone comfortable with predicting charge?
I'm kind of confused on how we got the 8 for that one.
So for non-metals, the charge preferred for a main group non-metal is equal to the group number minus 8. And this stems from the fact, so if we write out the configuration for iodine, it would be krypton 5s2 4d10 5p5. So we have 7 valence electrons to work with. And in order to go to the closest noble gas, which would be krypton 5s2 4d10 5p6, how many electrons would we need to gain? How many electrons would we need to gain?
1.
Yep, exactly right. And that's why we adopt a charge of -1, because we gained 1 electron during ionization. Does that make sense?
Yes, thank you.
Perfect, perfect. So we're at the end of chapter 2. So the quiz and homework for chapter 2 are going to be due Sunday. What we're now going to do is we're going to switch gears. I'd like you to get out your chapter 3 notes, and we're going to start on chapter 3, which covers bonding, molecular shape, and molecular polarity, as well as naming and classifying ionic and covalent compounds. So, just to make sure in the chat, is everyone able to, the chapter 3 notes again are available on Canvas. Is everyone able to access the chapter 3 notes? Is everyone able to pull up the chapter 3 notes from Canvas?
Yes.
Perfect, perfect. So let's get started then, and let's talk through chapter 3. So let's have a little bit of review first, and let's talk about elements. So here's the periodic table. There are our metals, which are in the majority of the periodic table, but primarily occupy the bottom left-hand side. The metalloids, which occupy the dividing line between the metals and nonmetals, and the nonmetals, which are primarily in the upper right-hand side of the periodic table. Now, the reason why I'm talking about metals, nonmetals, and metalloids right now is because it gives us the tools to begin to write out element formulas. So our atomic elements, as we discussed from chapter 1, are primarily metals and noble gases. Atomic elements have formulas with just a single atom. So for example, sodium, which is a metal, has a formula of sodium solid, just one atom in the formula. Likewise, helium, which is a noble gas, also exists as an atomic species where we have one atom in the formula. Does this make sense to everyone? Does this look like review to everyone from our section where we talked about formulas? So the other type of species are molecular elements. One moment. And if you have a question, don't be shy to unmute and ask. For our molecular elements, these consist of our nonmetals and metalloids. And molecular elements can be broken into two categories. Our diatomic elements, which consist of two atoms, which are primarily our halogens, oxygen, nitrogen, and hydrogen. So for example, hydrogen in its element form, or its elemental form, exists as H2 gas. Likewise, halogens. What's an example of a halogen? What halogen should I write the formula for?
Chlorine?
Chlorine, sure. So chlorine would exist as Cl2 gas. Halogens are diatomic. Likewise, fluorine is diatomic. Two atoms in the formula. Does that make sense? Is everyone comfortable with this? Does everyone remember these ideas? The last subclass of molecular elements are polyatomic elements that have 3 or more atoms. So for example, sulfur exists as S8, while phosphorus exists as P4. Those are the only 2 polyatomic elements that I'm expecting you to memorize. Any questions on the common formulas of elements? If not, let's look at the physical states. How do we write the physical states? Well, the state symbol indicates the physical state of each substance. S for solid, L for liquid, G for gas, and AQ for aqueous, which means dissolved in water. Metals are solids at room temperature. So sodium, aluminum, zinc are all solids. Iron also would be a solid. Magnesium also would be a solid. There's one exception, and that's mercury, which is a liquid. For our nonmetals, the noble gases, hydrogen, nitrogen, oxygen, fluorine, and chlorine are all gases. So for example, hydrogen would be written as H2 gas. Noble gas, what noble gas should we discuss? What noble gas? Neon. Noble gases are atomic elements and they're also gases. That's in the name. Okay, most of these common gases can be easily rationalized since they're components, either components of the air that we breathe, or they're the two halogen gases. There's one nonmetal that is a liquid, and that is bromine. Bromine is a liquid, so Br2 is a liquid. Most other non-metal and metalloid elements are solids. So if the state symbol isn't found in one of these early lists, it's likely a solid. So for example, S8 is likely a solid. Iodine, likely a solid. Does this make sense to everyone? Does this review look familiar? Okay, now there's one, yes, did someone have a question?
No, sorry, I was just delayed in saying yes.
No problem. So there's one word of vocabulary that I'd like you to be familiar with. Allotropes describe multiple distinct chemical formulas of an element with the same physical state. So for example, if we think about oxygen, oxygen is commonly written as O2 gas. This is known as oxygen. However, there's another allotrope, another formula of oxygen in the gas phase called ozone. And you certainly can't breathe ozone. It's quite a reactive molecule. And you can commonly notice that the presence of ozone via this almost musty smell during a thunderstorm, etc. So as we notice, both of these species represent the element of oxygen. We only have atoms of oxygen in our formula, but they have a different formula. Does that make sense? Same element, different formula. Any questions before we move on to the next topic? Okay, so let's talk a little bit about ionic and covalent compounds. So a compound, just as a review, is a substance containing two or more different elements. Compounds can be either ionic or covalent. Now, ionic compounds are compounds consisting of a positively charged cation and a negatively charged anion. what this essentially boils down to is most ionic compounds are composed of a metal cation and a non-metal anion. An example of this would be sodium chloride, NaCl, where we have our sodium cation, which is Na plus, associated with our chloride anion, which is Cl minus. So we typically have a metal and a non-metal in an ionic compound. It doesn't have to be a 1-to-1 ratio. So for example, aluminum sulfide is also an ionic compound. And we can tell that because we have a cation, a metal cation and a non-metal anion. So this metal non-metal pairing is a signpost that you have an ionic compound. Does that make sense? Is everyone comfortable with that idea? So a polyatomic ion is a charged molecular ion containing 2 or more atoms covalently bonded together. So what do I mean by that? So a common polyatomic ion would be cyanide, Cn minus. So it's a collection of atoms with a net charge. Other examples would be something like carbonate, where we have a collection of atoms with a net charge. So polyatomic ions are a collection of atoms covalently bonded with a net overall charge. Does this make sense? Perfect. So the formula unit is defined as the smallest repeating set of ions in an ionic compound. So for example, in aluminum sulfide, the simplest and the smallest repeating set of ions would be where we have 2 of our aluminum cations and 3 of our sulfide anions. Of course, this is a simplified picture. And essentially, this formula unit is repeated to give our overall structure. Now, as sort of a counterpoint to the ionic compounds, a covalent or molecular compound consists of 2 or more atoms of different elements covalently bonded together. And the signpost that we have a covalent compound is that we have 2 or more nonmetals in our formula, and we have a neutral species with no charged ions. For example, carbon monoxide is a classic example of a covalent or a molecular compound. We can get a little more complicated. Hydrogen peroxide would be another example of a covalent or molecular compound. In both cases, our formulas consist of 2 or more different nonmetals covalently bonded together. Does this make sense to everyone? So let's talk a little bit about chemical bonds here. So we know that ionic compounds consist of a metal cation and a non-metal anion. Well, an ionic bond fundamentally is a stabilizing interaction between a cation, such as, for example, sodium plus, and an anion, such as chloride minus. Now, opposite charges attract. And this attractive interaction between our two ions is very strong. Ionic bonds, this electrostatic attraction between positively and negatively charged ions is very, very, very strong. And we see this by the fact that the melting points are very high for a lot of ionic compounds. So we can see this by the fact that the melting point of ionic compounds, essentially the energy required to start to separate and dissociate this ionic bond, the melting point is very high. If we think about covalent compounds, as we discussed, are composed of two or more nonmetals. And a covalent bond is the sharing of outermost electrons between two atoms. Keyword, sharing. So for example, trying to think of one that's a little, let's do water. Yeah, so in water, we have the sharing of electrons between hydrogen and oxygen, and these shared electrons are known as a covalent bond. Covalent bonds, sharing. Ionic bonds, positive charge likes negative charge. Okay, covalent bonds are stable, but they're weaker than ionic bonds. The reason why a covalent bond is stable at all is that electrons shared between atoms are stabilized by the nucleus of each atom. So if we have two nuclei, so if we have the nucleus, which is primarily just a ball of protons and neutrons, and we have our electrons, these are our shared electrons, these are bonding electrons. These bonding electrons are stabilized by each atom's nucleus. So it's beneficial to share electrons because those electrons are able to interact with and be stabilized with both nuclei for each atom. Is everyone comfortable with the idea of ionic and covalent bonds? Any questions? So let's talk a little bit about electronegativity. Let's talk a little bit about electronegativity. So what is electronegativity? Electronegativity is a measure of how readily a nucleus attracts electron density in a chemical bond. How strongly does your atom pull electron density towards itself in a chemical bond? So if I had to draw an arrow for electronegativity trends, electronegativity increases going up and to the right on the periodic table. The most electronegative element, the king of electronegativity, is fluorine. Now, what does this mean? Well, depending on the electronegativity, your atom will pull electron density in a bond more or less effectively. So electronegative elements, such as nonmetals, prefer to form anions. That's why fluorine, in general, prefers to form the anion of F minus. It wants to gain electrons. It's very electronegative. Less electronegative elements, such as metals, prefer to form cations. Less electronegative elements would rather lose their electrons. They don't hold on to their electrons very strongly. That's why something like aluminum, for example, would much rather form a cation, such as aluminum 3+. So as we see, electronegativity can be thought of as a measure of how readily does your atom pull electron density towards itself and how readily does your atom hold on to electron density. Does this make sense to everyone so far? So you don't have to memorize the electronegativity table, but you should know the trend, that arrow that I've drawn. Any questions before we move on from this section? Okay, let's keep going. So let's look at electronegativity and chemical bonding, because yes, francium would be one of the least electronegative elements. So we're going to define a term called delta En, which is known as the difference. Just for your future science classes, when you see delta, this delta symbol, think difference. Delta En is the difference in electronegativity between two atoms in a bond. And the difference in electronegativity between atoms in a bond determines whether we have an ionic, a polar covalent, or a pure covalent bond. So, if their difference in electronegativity is small, less than 0.4, we have a pure covalent bond. This primarily occurs in two cases. The first case is if you have a carbon-hydrogen bond where your difference in electronegativity is around 0.2. What this pure covalent bond is trying to show is that a pure covalent bond has an even sharing of electrons. We have an even sharing of electrons. So if we think about a carbon-hydrogen bond, you can think of it as if our electrons are going to be shared equally between atoms. So this is our first case. Our atoms aren't very electronegative. There's a small difference. The second case can occur where we have very electronegative atoms. So for example, if I bond two fluorine atoms to each other, you may say, well, what's going to happen? Well, the difference in electronegativity, if we have identical atoms, if these atoms are identical, the difference in electronegativity is going to be 0. So even though our two fluorine atoms are viciously electronegative, they both pull on our electron density with the same strength. Think of electronegativity sort of like a tug of war game. The more electronegative your element is and the greater your difference in electronegativity, the more your electrons are going to be pulled towards one of your atoms. And the more your compound will, rather than resembling an even sharing of electrons, start to resemble an uneven sharing. Does that make sense? Does everyone understand the idea of a pure covalent bond? We have an even sharing of electrons. Any questions in the chat? So Let's look at what happens when we start to develop a difference in electronegativity that's greater than 0.4. This is known as a polar covalent bond, and in turn, we have an uneven sharing of electrons. So, for example, suppose we're looking at a carbon-oxygen bond, which has a difference in electronegativity around 0.6. What you just need to know is that that oxygen is farther to the right than carbon. You don't need to know the exact electronegativity numbers, just the trends. So if we think about our carbon-oxygen bond, which atom is more electronegative? Which atom is pulling on our electron density more readily? Which atom is more electronegative? What was that?
Oxygen.
Yep, exactly right. Oxygen is more electronegative. And as a result, in our carbon-oxygen bond, most of our electron density is going to be centered on oxygen. Now, if oxygen now suddenly has excess electron density, what are electrons fundamentally? Are they positive or negatively charged? What was that?
Negative.
Yep, exactly right. So then, because we have excess electron density, we end up building a partial negative charge. So our oxygen starts to adopt and starts to gain a partial charge because it has excess electron density. Likewise, our poor carbon atom is electron deficient. And if we lose electron density, if we lose some of our electron density, what partial charge will we generate? Positive or negative? What happens if we lose some electrons? If we lose some electron density, we start to develop a partial positive charge. And this separation of charge is known as a dipole. And to represent a dipole, we draw an arrow pointing towards our more electron rich or our more electronegative element. So we call molecules with an uneven distribution of electron density and a separation of partial charge, we call these molecules, quote unquote, polar covalent molecules, or bonds that are polar covalent bonds. Does this make sense to everyone? So, the last major type of bond occurs if we have a large difference in electronegativity. If we have a difference in electronegativity greater than 2.0, this primarily occurs when you have a metal and a non-metal. So for example, sodium and chlorine, we have a difference of electronegativity of around 2.2. Metal, non-metal, that's a signpost for an ionic bond. Now, why is that? Well, sodium, it's very weak at it doesn't want to really hold its electrons that much. It has a very low electronegativity. Chlorine, on the other hand, really wants electron density. So chlorine is so overwhelmingly electronegative that rather than a sharing of electrons, we just have chlorine, quote unquote, steals the electrons from sodium. So rather than a sharing of electrons, we instead have a transfer of electrons to generate ions. So we, instead of having neutral species, we have instead a cation and an anion, sodium plus and Cl minus, engaging in an ionic bond. Does that make sense? Any questions on these three different types of bonding? If not, let's keep going and let's talk about periodic trends and ions. So metals typically lose electrons to make cations. So your main group metals will form a cation with the charge equal to the group number. So for example, magnesium, which is a 2A element, would like to form the cation magnesium 2 plus, because the group number is 2. The next, let's look at another example. Lithium, which is a 1A element, will prefer to form lithium plus because the group number is 1. Boron, which is a 3A, well, yeah, that's fine, will prefer to form boron 3 plus. Does this look familiar to everyone? Is everyone comfortable with these trends for ionization for metals? Let's look at our non-metals now. So non-metals prefer to gain electrons to make anions, and non-metals form anions with a charge equal to the group number -8. So for example, nitrogen, which is a 5A element, 5 minus 8 gives us -3. So nitrogen prefers to form nitrogen 3 minus. Sulfur, which is a 6A element, 6 minus 8 is -2. And oxygen forms O2 minus. Bromine, which is a 7A element, 7 minus 8 gives us -1, and bromine prefers to form Br minus or bromide. Does this make sense? So let's talk about transition metals. Transition metals typically can adopt a +2 charge. So iron can go to iron 2 plus, but they can adopt a range of positive charges. So iron can just as easily go to iron 3 plus. So you can't really predict the charge of a transition metal without additional information. So you can't apply the same rules for main group elements to transition metals. However, there are some exceptions. These are known as fixed charge transition metals. You'll need to memorize these. Silver, cadmium, and zinc form silver plus, cadmium 2 plus, and zinc 2 plus. These fixed charge transition metals are important to be familiar with as they really set the stage for writing out and they're really important in terms of the rules for writing out the names and formulas for certain ionic compounds and transition metal containing compounds. So, any questions so far? Okay, so let's take a moment and let's predict the charge of the ion formed from each of the following atoms. So let's take about 3 to 4 minutes and work on this example, and then we'll come together as a group to discuss. And don't be shy to share your questions or your responses in the chat. And if you have any questions, don't be shy to ask them in the chat. And we're already starting to see some reasonable responses in the chat. And we'll discuss this example in about another 1.5 to 2 minutes. Let's try to get a few more responses in the chat, just so that way we have a diverse pool of student responses, and so I can provide feedback to the entire class as effectively as possible. And let's try to get a few more responses in the chat before we discuss. Okay, so let's discuss. So magnesium is a group 2A element. So magnesium would prefer to form magnesium 2 plus. Sulfur is a 6A element. Sulfur would prefer to form 6 minus 8 minus 2, which is sulfur 2 minus. Silver, it's a fixed charge transition metal, so it will prefer to form silver plus. And nitrogen, being a 5A element, 5 minus 8 gives us -3, and nitrogen prefers to form nitrogen 3 minus. Do these examples make sense so far? Do these examples make sense? Any questions on this first set of examples?
Just real quick, how do we know when we subtract? Is it anything past like 5?
So for your non-metals. So anything on the right-hand side of the periodic table, well, for your metals, which are everything on the left-hand side of the periodic table, you just take the group number. Does that make sense?
Yes.
Perfect. So with this information in mind, I'd like you to tackle now the following examples. And I'll do scandium for you. Scandium prefers to form scandium 3+. That one's a little bit tricky. Let's focus on these first 3 as they're examples that you're likely to see on an exam. So let's work on these first 3 and then we'll discuss in about 2 to 3 minutes. And we're already starting to see some reasonable responses in the chat. Let's keep working on this example and we'll discuss in 2 minutes. And don't be shy to submit your responses in the chat. Even if your responses are different from your classmates, the more the responses that I have to look at, the more I can adjust my feedback or design examples to help clarify any questions or concerns that you have with this material. We'll discuss in about another minute. Okay, so bromine is a 7A element. It's a non-metal. So 7 minus 8 gives us -1. And bromine prefers to adopt a -1 charge. Lithium is a 1A element. So it prefers to form lithium plus. Zinc is a fixed charge transition metal, and zinc prefers to form zinc 2+. It is our one of our 3 exceptions. It's a fixed charge transition metal. Do these examples make sense? Okay, let's keep going and let's talk about valence electrons and bonding. So atoms typically lose or share their most readily accessible electrons and highest energy electrons, otherwise known as the valence electrons. The valence electrons are defined as the electrons in the highest energy principal energy level, the electrons with the largest N value. And that in turn leads us to a really important rule known as the octet rule, where atoms will gain, lose, and share electrons to reach noble gas configurations, 8 valence electrons. Now, to help us with this, the reason why we teach abbreviated electron configurations is that abbreviated electron configurations can be used to identify the valence and core electrons. So if we look at the abbreviated electron configurations for different elements, we can begin to notice a really important trend. So let's just review this. So chlorine would have an abbreviated electron configuration of argon 4s. Oops. Sorry, I'm thinking of bromine. One moment. Chlorine would have the configuration of neon 3s2 3p5. So how many valence electrons does chlorine have as a 7A element?
7.
7. Exactly right. So what I'd like you to do is I'd like you to write the abbreviated electron configurations for these 3 elements, and I'd like you to identify the valence electrons. And we'll discuss this example in about 3 minutes. And don't be shy to submit your proposed abbreviated electron configurations in the chat and to provide your valence electron counts in the chat. And we'll discuss in about another 2 to 3 minutes. Let's try to get a reasonable pool of responses before we discuss this next set of examples. And we're already starting to see some reasonable responses in the chat, but don't be shy to submit your own responses, as having a range of student responses allows me to get a greater sense of the class's perspective on each of these problems. And we're seeing a nice pool of responses so far. We'll discuss this example in about another minute to a minute and a half. And it's great that we have a range of students in the class participating and submitting their responses. So for bromine, as the class has very astutely pointed out, it's a 7A element and has a configuration of argon 4s2, 3d10, 4p5. Only our outermost electrons are valence. So bromine has 7 valence electrons. Lithium has the configuration of helium 2s1, and as a 1A element, we have 1 valence electron. For carbon, which is a 4A element, has a configuration of helium 2s2, 2p2, and in turn, we have 4 valence electrons. Does this make sense? Everyone comfortable with this example? So, main group elements have valence electrons equal to their group number, right? And we care about valence electrons because they're responsible for bonding and engage, and they're the electrons that are exchanged, gained, lost, shared in chemical reactions. So one thing that we can do is we can abbreviate the valence electrons in what are known as Lewis dot structures using dots to represent electrons. So one dot, one valence electron. So lithium, 1A element, one valence electron, one dot. Beryllium, 2A element, two valence electrons, two dots. And so forth. Now, the beautiful thing about this list is that as elements in the same group have the same number of valence electrons, this line of 8 different Lewis dot structures describes all of the main group elements that you'll encounter. So let's see what I mean by that. I'll do the first example. So for chlorine is a 7A element, 7 valence electrons. So how many dots do I draw? How many dots do I draw? 7. 1, 2, 3, 4, 5, 6, 7. There we go. So what I'd like us to do is in the next 2 minutes, I'd like everyone to identify the number of valence electrons in each of these structures. And if you notice the little black tab under Zoom meeting options, there's an option called annotate in the drop-down menu. I'd like if someone would be willing to try annotating their proposed Lewis dot structure. If not, you can share in the chat the number of valence electrons for each of these 3 atoms. This is a really important skill that we're developing. So let's take about 2 minutes to make sure we're all on the same page. And if you have any questions, don't be shy to ask in the chat. And it's good that we're getting a pool of responses. And we'll discuss this example in about another minute. Perfect. Someone is able to share their responses with the annotate feature. This is wonderful. Perfect. And that depiction of bromine looks great. And if anyone would like to share using the annotate feature, the Lewis dot depiction of some of these other 2 atoms, that would be awesome. Otherwise, we'll discuss in about another minute. And it looks like we have another proposed response for sodium. And it's great that we have a pool of responses from different members of the class. Perfect. So we have a nice, reasonable pool of responses from different students in our class. They all look great. So let's just clear it so I can provide the instructor solution so it shows up on our note set. So bromine is a 7A element. So bromine would have 7 valence electrons, 7 dots. Sodium is a 1A element. So sodium would have 1 dot. Silicon is a 4A element, so silicon would have 4 dots. And no, it doesn't matter where you put the dots. It's mainly just a way of keeping track of the number of valence electrons. Does this example make sense? Is everyone comfortable with representing atoms in Lewis dot structures? Okay, so just to remember, elements in the same group have the same number of valence electrons. And the nice thing about Lewis dot structures is that they make it really easy to visualize gaining and losing electrons. So just as a reminder, the octet rule, atoms will gain, lose, or share electrons to reach noble gas configurations. Your 1A through 3A elements form cations with charge equal to their group number. So sodium in Lewis dot form looks something like this. So to reach a noble gas-like configuration, we just need to lose this 1 electron to generate sodium plus. Likewise, we remember that 5A through 7A elements form anions with charge equal to their group number. So for example, chlorine, which has 7 valence electrons, in order to have a complete octet, all we need to do is gain 1 electron. And that in turn gives us chloride, Cl minus. This is part of why Lewis dot structures are pretty nice, is they give you a really nice visual method of tracking, gaining, and losing electrons. As we notice, the resulting cation or anion has a noble gas configuration. In this case, 8 valence electrons. Transition metals typically lose their s orbital electrons to give cations. That's why most transition metals adopt a 2+ charge as they lose their s electrons. In many cases, you can lose the outermost s and d orbital electrons. So for example, for scandium, as it's pretty early in our set of transition metals, has the configuration of argon 4s2 3d1, and it can lose these valence electrons to form scandium 3+. Does this refresher make sense to everyone? Does this refresher on common ionization trends make sense? Okay, so let's talk about ionic bonding and electron configurations. So one thing to keep in mind is that when you think about the dot structure for a cation, you're going to lose electrons equal to the charge. For anions, you gain electrons equal to the charge. So what I want us to do as our last exercises, I'd like you to show the Lewis dot structure for each atom and each ion. So in this case, I'd like you to draw the Lewis structure for calcium and then show the Lewis structure for the ion formed from calcium. I'll do this first example and you'll do the second involving cesium and phosphorus. So calcium is a 2A element, starts off with 2 valence electrons. If we lose our 2 electrons, we generate calcium 2 plus. Sulfur as a 6A element has 6 valence electrons. And if we gain 2 electrons, we'll generate sulfur 2 minus, which has a full valence shell. I'd like you to draw out the Lewis dot depiction for cesium and phosphorus and show the Lewis dot structures for the ions formed from cesium and phosphorus. Does this make sense to everyone? So let's work on this example for about 3 minutes and then we'll discuss. And we already have someone sharing their response using the annotate tool. Don't be shy to share your own annotation if you'd like to chime in with your response for phosphorus. So it's very close, but remember when we gain electrons, do we adopt a positive or negative charge?
Negative.
Exactly right. So the response looks great. I'm just going to clear the drawing and let's write out the instructor solution. So cesium is a 1A element, so it has 1 valence electron. We'll lose 1 valence electron to make cesium plus. Phosphorus is a 5A element. So it has 5 valence electrons. In order to complete the octet, we need to add 1, 2, 3 electrons. And that in turn gives us phosphorus 3 minus.
Professor, I don't understand the gain and the loss. Like, where do we get that from?
Well, so metals such as cesium prefer to lose electrons, and non-metals like phosphorus prefer to gain electrons. And we gain or lose electrons to reach an octet, which is 8 electrons total.
Okay,
that make
and
sense?
where do we get like the 3, for example?
So
Plus 3.
so we have 5. How many do we need to add to get 8?
Oh, 3.
Yep, exactly right. Does that make sense?
But how do you know where to start? Like, you're looking for 8 electrons, so where do you look for that? Is that where do we get the 8 from?
So this is based on the octet rule. And in general, atoms prefer to gain, lose, or share electrons to reach 8 total valence electrons. 8 total electrons in their outer shell.
Okay.
Does that make sense?
Yes, thank you.
Perfect, perfect.
So
So,
for cesium, because it's a metal, we lose an electron?
yes, exactly right. And you can draw cesium like this as well, because we've lost our outer shell and now we have our full inner shell on display.
Oh, okay.
Does that make sense?
Yes.
Perfect. So we're at the end of today's scheduled lecture.